Hello, everyone. This is the lecture for the next week, the week that you're about to have. So instead of going to class on Monday, your job is to look at this and to make sure you actually watch all the video. I'm going to innocuously just pepper in things you need to know to get full credit next week. So do please watch this video. I've tried to make it as short as possible, so it's actually going to be different from my typical lectures. I'm not going to go through lengthy explanations. I'm going to go through the quickest, most direct, logical explanation with the understanding that you have the time to pause and rewind and do whatever you have to do to understand that explanation. You do want to make sure you understand every step of it, but like I said, I've tried to make it as concise as possible. And of course, I will be including examples of harder, more complicated, and illustrative problems. Okay, so what we're going to be talking about today, well, for this week, are sections 5.1 and 5.2. I don't believe I'm going to be talking about 5.3 this week. I don't think it's realistic to get through that, even though the schedule says we should be through it. So I already started talking about 5.1 last time, and I discussed the idea of thinking of angles not just as a measure of the difference in direction between two lines, where this would be a small angle, this would be a big angle, but also thinking of angles as revolutions. I talked about the difference between the two primary measurements that we use for angles. So with the degree system, a full rotation corresponds to 360 degrees. In radian units, a full rotation corresponds to 2 pi radians. One more system of units, although it's not really a system of units, it's more just a natural way that we think about things, is revolutions. And so one full rotation is just one revolution, right? That's sort of the simplest possible unit you could use. And if we go through here and we actually use the conversion formulas, what would our conversion formulas look like between these units? Well, 360 degrees is equal to 2 pi radians is equal to 1 revolution, right? And what's nice about radians, I started to talk about this in some of your classes, but not all of them, so forgive the overlap if you were one of the people who has an overlap. But what's nice about the radian system in particular is the way certain formulas, certain geometric formulas work out. So let's look at, first of all, let's look at this conversion formula right here. By dividing both sides of this equation by 2 pi, I can see that theta radians corresponds to theta divided by 2 pi revolutions, right? That being the case, I can now easily compute both the arc length of the circumference, of the portion of the circumference which is cut out by an angle theta, and I can also figure out the area of a sector here doing this. And the basic idea is this. The length of this subarc of the circle, which is cut out by an angle theta in radians, is given by the formula S is equal to theta over 2 pi, which corresponds to the fraction of a revolution I've completed around the circle, times the full circumference of the circle. After simplifying that formula down, I see that it becomes just theta times r. So that's where our first formula tells you, and this is also why we like radians. They're the unit which makes this formula work out very nicely. In particular, if r is equal to 1, so that we're on a unit circle, the radian measure of an angle is precisely the subarc length of the circle that is swept out by that angle. The area formula looks a little bit more complicated, but it's not that bad. Okay, once again, I just take the full area of the circle, I multiply it by the portion of the circle that is swept out by the angle theta in radians, and after simplification, I see that the area of just this sector right here is given by theta over 2r squared in radians. Now, as one helpful extra credit exercise, or not even extra credit exercise, it's just as an exercise. If you want an exercise to do to make sure you've understood this derivation, find the formulas for sector length and area in terms of degrees. You'll find out that those measurements are different, and make sure that you can find those, and you'll know for sure that you've understood this little derivation of the formulas and why they're true. Up next, I'm going to talk about applications of these formulas. Okay, so I've changed my mind. I'm not going to go straight into application. The first thing I realized might be a good idea to do is if you did actually try to derive the formula for the arc length and the sector area in terms of degree units instead of area units, if you tried to do that instead of using radians, then you might be interested to know what the answer is. So here I will derive that answer. This is not an important formula for you to know, but for those of you who are interested in knowing, who tried it and who are interested in knowing whether their answer is right, here is the correct solution. So the portion of the circle that is swept out by theta degrees, by using this conversion formula, is just 1 over 360, theta over 360 revolutions, right? And so therefore, when I'm trying to figure out what this arc length is, S, it is just equal to the portion of the circle swept out by theta degrees, which is theta divided by 360, times the full circumference of the circle, which is 2 pi r. This doesn't simplify to anything particularly nice other than theta pi r over 180. Similarly, the area of the pizza slice here is given by theta over 360 times the full area, which is pi r squared, and this doesn't simplify at all. So we see here that it is possible to derive formulas for the arc length and the area in terms of degrees, or really any units, using this conversion I talked about, but radians is the unit where things work out most nicely. Okay, so here's our first very simple application type of problem that these formulas can be used on. So I've drawn a pizza slice and just pretend like it's a perfect sector of a circle. So the outer edge here is part of a circle of radius 5 inches. It might be hard to see here. I want you to understand that this is 5 inches. Okay. So the interior angle of the pizza slice is 27 degrees. Its length is 5 inches. You are required to find the perimeter and the area of this thing. So first, let's start with the perimeter. So the perimeter is, of course, composed of 3 parts. This side, and this little piece here. Of course, the first sides don't require any mathematics. The 2 straight sides are just 5 plus 5 inches plus the length of the round side. So the only part that requires any work is finding the length of the round side. And of course, to find the length of the round side, we have a nice formula. Again, according to our formula for sectors of a circle, if I have any circle of radius r, and I want to figure out this arc length s, is just given by s is equal to theta times r. The one thing that we want to be aware of, though, is that theta has to be in radians, and we're given our angle in degrees. So, we must convert theta into radians like so. So, we remember that 180 degrees is equal to pi radians. Therefore, 27 degrees corresponds to pi over, well, 27 times pi divided by 180 radians. And so after some simplification, we will write theta is equal to 3 pi over 20 radians. Once this is done, we see that our S here is equal to 3 pi divided by 20 times 5 inches. And so our final answer is that our perimeter is equal to the 10 inches plus the 3 pi over 20 times 5 inches. This comes from the straight sides. This comes from the round side. And that is the ultimate solution to our equation. So again, we're going to use the fact that 27 degrees is equal to 3 pi over 20 radians for the second problem as well. And it's going to go even easier. Using the formula directly, we know that the area of this little pizza slice is just theta divided by 2. So it's 3 pi divided by 20. And instead of dividing by 2, I'm going to multiply it by 1/2 times r squared, which in this case is just 25 inches squared. And that's it. We can simplify this down a little bit. You can plug this into your calculator if you want. But that's pretty much all there is to these problems. Just plug and chug. Just be careful that you make sure that you convert from degrees to radians first so that the formula doesn't get you wrong.